Hello everyone, and welcome back to another remote sensing lecture video. And in this lecture video, we're going to wrap up our discussion on the dimensions of remote sensing. So just to quickly recap, we talked about the spatial dimension or spatial resolution, which dealt with the size of a pixel. We dealt with the spectral resolution, which was the number of bands and the sensitivity of those bands. We talked about the temporal dimension or temporal resolution, which was talking about how often are we able to get the same data set. And now we're going to wrap up by talking about the radiometric dimension or radiometric resolution. And this one I think it's very important, but it's often underrepresented in this discussion. And so as always, we're going to start off with a quick, just one sentence description. And radiometric resolution, just in one sentence, talks about the range of possible values a pixel can have. And again, tying this back into that idea of the remote sensing data structure, right? We've talked about the size of a pixel, we've talked about the number of bands. Now we're going to talk about what's actually inside of a pixel, the data value. And radiometric resolution, again, talks about the range of possible values that the pixel can have. Okay. So let's start off our discussion here about the radiometric dimension. Right, the radiometric dimension of remote sensing. And so just to recap, right, this is the range of possible data values a pixel can have. The range of possible values a pixel can have. And so without getting too much into the math, when we talk about radiometric dimension, what we're really talking about is what's called bit depth. Right? And so bit depth is the number of bits per pixel. And so for those of you that aren't familiar with binary or computer science, right, a bit is a single digit in binary. And so if, for example, if something is 1 bit, it can be either 0 or 1. Right. So, for example, actually, let me erase that. So, for example, if something is 1 bit, right, it can be either 0 or 1. Something is 2 bit, right, that's 2 to the 2, which is 4. So that means something can either be 0, 1, 2, or 3. Right? There are 4 possible options that you can get out of a 2-bit image. So that means that the pixel, right, when it's recording a value, regardless of how much radiation's hitting it, right, because the first thing that's measured is always that radiance, right, when the sensor gets excited by the incoming radiation, Right? It has to decide, well, is this amount of radiation going to be a 0, 1, 2, or 3? And those are the only 4 values that it knows and can assign. Right? And so if it's hit by radiation, right, it can only be 0, 1, 2, or 3. Right? That's what it means when it's 2-bit, because it's 2 raised to the power. So we can generalize this, and we can say that the bit depth is measured as 2 to the n is the bit depth. Right. And so we could just really quickly go through 3-bit, right? That'll be 2 to the 3rd, which is equal to 2 times 2 times 2, which is 8. So that means we have 0, 1, 2, 3, 4, 5, 6, or 7. So now when energy hits, when a pixel on the image gets excited, right, it's either a 0, 1, 2, 3, 4, 5, 6, or 7. So we already have more choices than we did in 2-bit. And so you may be asking yourself, well, why does this matter? Why does bit depth matter? And what I want to do is I want to walk through some examples showing you why bit depth matters. So what I want to do is I want to start over here. So what we've done is we've taken an image. This is one band of sentinel imagery. So this is 10 meter spatial resolution. This is one band. And I've started out by converting it to 8-bit. Right, so this is 8-bit imagery. And if we go from 8-bit down to 4-bit, you can already see that we've lost a lot of detail in terms of the radiometric value options, right? The pixel value options. A lot of things now have been converted to this dark gray and this medium gray. A lot of the nuances in the fields and in the buildings have been lost. So let's look what happens as we go from 4-bit down to 2-bit. So again, in 2-bit, our option is 0, 1, 2, or 3. And you'll see that one of those options, right, has been dedicated to this no data border that we have here. So we really only have 3 options. And you can see that the options are this light gray, dark gray, and black. So you can see how going from 4-bit to 2-bit, we've lost even more of that detail. Right, the smallest change, detectable change in radiation. And then again, just to show going from 2-bit down to 1-bit, now we've got the very bright pixels and the border, and then everything else. So again, just to sort of reiterate here, as you decrease the bit depth, as you decrease the radiometric resolution, you force pixels to fall in the same data pixel value, even if they're not even close in terms of the amount of radiation that they're giving off. But we can formalize this a little bit better, I think, to answer the question of why does radiometric resolution matter? Right, and we can formalize this, I think, very nicely by saying, it controls the smallest detectable difference in radiation between pixels. Right? And so just to reiterate that, right, as you increase the bit depth, right, as you go from 2-bit to 4-bit to 8-bit to 12-bit to 16-bit, right, the sensor has more options, right? It has more values available to it, so that when 2 pixels get excited by radiation, the sensor is able to say, okay, well, this one's slightly higher, I have slightly more radiation. I'm going to give it a slightly higher pixel value than the pixel next to it. As you decrease the radiometric resolution, right, as you go down, you go from 8-bit to 4-bit to 2-bit, suddenly it looks at those 2 pixels and it says, well, I don't have enough choices. These are going to have to be given that same value, even though they're still technically different in terms of the amount of radiation that was present. The sensor just doesn't have the fine scale number of options as you do if you increase the radiometric resolution to something like 12-bit or 16-bit. And so what I want to do to wrap up this discussion is I want to wrap up this discussion like I do all of the discussions so far, of saying, why isn't all imagery, I'm just going to throw out something like, say, 64-bit. Right, why isn't all imagery 64-bit? Now, just to sort of preface this, most imagery is somewhere between 10 and 16-bit. Operating systems are 32 or 64-bit. But why isn't imagery 64-bit? And there's really 3 reasons. The biggest one is data volume. All right, and we've talked about data volume time and time again. Because you have to remember, right, this radiometric resolution, this is for every pixel in every band. So as you increase the radiometric resolution, right, you're increasing that sensitivity in all the bands. Right? It has more options in blue, it has more options in red, it has more options in green. And every time you increase the number of options, you increase the data volume because you're increasing the range of possible values that it has to store. So as a general rule, right, as you increase radiometric resolution, right, as you increase that bit depth, you increase data volume. And this can be pretty substantial. So you don't want to have 64-bit because the file sizes would just be so large, they would be unmanageable. 2 is cost. Right? If you want a 64-bit image, right, the sensor that collects that is going to be far more expensive to make than something that can collect imagery at, say, 12-bit. So as a general rule, right, as you increase the radiometric resolution, you increase the cost of the sensor. And then finally, I might actually not even write this down here, but finally, you have to realize that a lot of computers just aren't built to handle things higher than, I said here, 64-bit, but we could technically go higher than that, right? It's possible, but computers aren't really designed to handle information higher than 64 bits. You start to run into issues inside of your computer just not being able to handle it. So why don't we always have the highest possible bit depth? It's really because of data volume and cost. And also after a certain point, you get diminishing returns. Right? If you go from 16-bit to 32-bit, you already have a lot of options at 16-bit. And if you go to 32-bit, is it really going to increase the quality of the data that much? And the answer is probably not. So typically you end up somewhere between 12-bit and 16-bit. So again, if there's anything you didn't understand, if you have any questions, I encourage you to pause, rewatch the video, and as always, reach out.